So let me finish this dependent random choice part by one more application, a slightly more complicated application in Ramsey-Turan theory. So last time we mentioned that there is this so-called phase transition that recall last time that we proved that there is a construction showing that for K4 free graphs, if the independence number is larger than some constant times n square root n log n, I think constant 1 is good enough, but please check, maybe 1.5. Then this is number of edges we can get is n squared over 4. Whereas if the independence numbers drop below square root n log n, there's a transition to density 0. Whereas this K5, if you are little o of n square root n log n, then this is little o n squared. Okay. This is a result of Balog, Pinghu, and Shumanovich. In the same paper, they asked the following question. Let me see. So they observed that it's also known. They want to know for larger clique, how does its Ramsey-Turan number transit around this inverse function of triangle Ramsey number? So in particular, they asked about K8, the 8 clique. So it's known that when you're above this threshold of inverse function of triangle Ramsey, so if your independence number is allowed to be square root n log n, then the number, you can take a construction where the number of edges is n squared over 3 plus little o n squared. This is easy. You just simply take 3 parts, you put all edges in between, and you put this, you put inside each one of them. This is high girth and little o n independence number graph. Okay. Right. Then, because it's high girth, so it's triangle free, the best you can get is to get the edge inside. Then it's actually even K7 free. Okay. Now they asked this question of Balog, Pinghu, and Shumanovich. They asked what happened, what is when you drop below this threshold, little o of square root n log n. How much it drops? And this a while ago by Jae-Hoon Kim and Yoonjin Kim and myself, we answered this question. We proved that it dropped from n squared over 3 to n squared over 4, and we prove its equality. So I think this construction, what you can do is you can just take complete bipartite graph that has roughly n squared over 4 edges, and then now you put inside oh, I said something wrong here. What you don't put inside is high girth thing. That's not enough for the independence number. You need to put the triangle Ramsey graph. meaning you have a n-vertex graph, triangle free, independence number is at most square root n log n. Okay. Now instead here, we'll put the K4 Ramsey graph. We now know that there is this K4 Ramsey, so n vertex, K4 Ramsey, K4 free. Independence number is well, let me write it like this: n tilde up to polylog term n to the 1/3. So it's much below this threshold. It has this many edges. That's the lower bound. Let's prove the upper bound here. So the upper bound uses several tools. One of the tools is the dependent random choice. Let me state this part first. Here is the lemma. Lemma using dependent random choice. So one of the lemma is the following. We have, okay, now for the upper bound, let me state what we need to prove for the upper bound, okay? Upper bound, we need to show the following. Right, we need to show that for any theorem, this is the upper bound. For any gamma, there exists delta such that for any graph G, n vertex graph G, if it's K8 free, and if its independence number is little o of square root log n, so that's delta is the little o times square root n log n, then your number of edges cannot be more than n squared over 4 by little o n squared. Here the little o is gamma n squared. This is what we need to prove. Okay. Here's the lemma using dependent random choice. It says the following: you take any let me use beta. For any beta between 0 and 1, and now for any graph G, that's three-partite. Okay, with partite set, let me draw a picture. You have Z1, Z2, Z3. Each part of order n, three-partite, each Zi has n vertices. And there's a minimum degree condition from Z1 to Z2, Z3. Let me draw it. So every vertex here, they have mean degree linear to both sides for every vertex. Okay. So this is written as for every oops. So let's say V. For every V in Z1, its degree of V to Z2 and its degree to Z3 are at least, let's say, beta n, beta fraction. If we have this minimal degree condition, then what we can conclude is that you can then zoom into a still relatively large part of Z1. There exists a subset S in Z1, satisfying such that it's not too small. Let's say it's 1/2 n to the 2/3 size. Good enough for us. And every pair, so you can zoom into these, to these little parts. Oops. To this little part S. So this little part S has the property that every pair in there, they have linear co-neighbor in both parts of Z2 and Z3. Their co-neighbor is large. Maybe I should use a different color. So for every UV, maybe let me use a different symbol, XY in S, the degree, co-degree of XY. How do I write this formally? Maybe I should write the neighborhood of X in Z2 intersect the neighborhood of Y in Z3. Is at least beta to the, let's say, 9 times n. Okay, and this is true for Z2 as well on both sides. So we can boost. Initially, we have a mean degree condition to both sides. Now we have a mean co-degree condition for pairs for a relatively large set S. So this is proved by dependent random choice. I will leave as an exercise. Prove the above lemma using dependent random choice. Good. Suppose we have this lemma. Now, so once again, what does it say? You have a mean degree condition towards each part. Then you can zoom into a relatively large set that we have mean co-degree condition for pairs towards each part. We need to prove these, right? Now let's first apply regularity lemma. Assume we have a graph G satisfying these two conditions. Apply regularity lemma, proof of the theorem. First, regularity lemma, you get a reduced graph, R. So here I need to use a black box of lemma. Here's the black box. I will not prove it. Let's assume it for now. This is the black box. It says that for any n-vertex graph G with independence number at most n to the 0.99, then if there is a KR in the reduced graph, let's say KT in the reduced graph, by taking usual reduced graph, then the graph G will actually contain a K2T. Okay. We can apply it here because our graph G has independence number polynomially smaller than n. It's actually square root n roughly. So then applying the contrapositive of this lemma, we know that the reduced graph must be K4 free, because if we have a K4, we will have a K8. But our graph G is K8 free, right? So by this, we know that by the above lemma, G is K4 free. R is K4 free. Okay, very good. Now, now we want to use another black box, which I will not prove either, but it's interesting statement on its own for um, K4 free graphs. So here's a theorem. For every m vertex, so this type of statement is interesting on its own. There is plenty of research on this type. For every m vertex K4 free graph, if G, if the number of edges is at least n squared over 4 plus t for some non-negative constant t, then if t is 1, you know that there are at least one triangle, right? If t is 2, how many triangles? Well, many. But here we cared about finding edge disjoint triangles. So this theorem is saying that when you t above the extremal number for triangle and your graph is K4 free, which is important, then you can find t edge disjoint triangles. G. Okay. So after using these two black box, we can now finish the proof. Well, the first claim we need to, the key claim, let's define the claim is there is no triangle in the reduced graph. So remember this reduced graph where the vertices corresponds to clusters, these parts in the regular partition, and it naturally comes with weight, which indicates the density of the corresponding cluster. Now I want to claim that there's no heavy triangle. There's no, let's say, chubby triangle. So what does it mean in R? So what it means is, for every triangle in the reduced graph R, every edge in the triangle has weight, which, remember, corresponds to density between the pairs, has weight and most 2/3 plus some small constant gamma. So it cannot be larger than 2/3. Let's first finish the proof, assuming this, and then we come back proving this claim. So claim implies the theorem. Well, let's suppose, so let's say our reduced graph capital R has little r vertices. Let's say it has r vertices. Then suppose, then R is K4 free. Now suppose the number of edges in R equals to R squared over 4 plus t. Okay, for some t. T could be negative. If t is negative, we're done already, because this would imply E of G is smaller than n squared over 4 plus little o n squared if you apply the right constants. Essentially, the edge density of R is similar to edge density of G if you forget about the weights. If you view R as just graph, not weighted graphs. Good. So we may assume T is positive. If T is positive, then since R is K4 free, we can apply this theorem, which says that we can find many edge disjoint triangles. So may assume now T is non-negative. This implies by the theorem above that there exists at least T edge disjoint triangles in R. Okay. So that means what? That means the edge set of R can be decomposed into T. We can find T edge disjoint triangles. After remove T edge disjoint triangles, we remove 3 T edges. This contains 3 T edges total, right? So how many edges remained? We have this many edges minus 3T. So we have R squared over 4 minus 2T edges remained. Now let's count. We can now upper bound using this claim. For every edge, we just assume it's weight 1. For every triangle, though, we know that the weight is at most 2/3 for every edge in the triangle. So we get, by the claim, implies that E of G is at most. Let's first look at the edges, this term. The edges is what? R squared over 4 minus 2T, right? This number of edges. For each of these edge, we'll assume is equipartition, is n over R correspond to this many edges, plus, here comes this term, plus we have 3T edges in all these triangles, n over R. Each edge correspond to n squared over R squared edges. But remember, by the claim, the weight is at most 2/3. We need to multiply by 2/3 plus gamma. Okay. Now this equals to what? Let's collect the main term. So this basically just n squared. You have n squared over 4 minus 2T of this. Here, cancel out. This is roughly 2 plus gamma times T. So this is like 2T. And you have 2T, right, times this. This is low order term. So we have n squared over 4 plus some low order term. That's exactly what we want. N squared over 4 plus gamma n squared. Done. Okay. The question is why we have this claim. This is also easy. So now let's prove the claim. There's no chubby triangles in R, i.e., for every triangle in R, no edge in the triangle in the reduced graph can have weight strictly larger than 2/3. Proof of the claim. Suppose there is a triangle. Suppose not. Okay, what does it mean, suppose not? We have a triangle where this weight, the weight of this guy, is bigger than 2/3. Okay? Plus gamma, some low order term. Plus, you are strictly above 2/3. What does this correspond to? This corresponds in the graph we have. So if this is ijk, this corresponds in the graph. We have three classes, Vi, Vj, and Vk, such that you have all edges here. That means they are all dense and regular, but this part is particularly dense. So they are all pairwise dense and regular. And this part, the density, is strictly bigger than 2/3 plus gap, right? We're going to embed a K8 to derive contradiction. Well, first you do some cleaning. You can clean out some low degree atypical vertices from Vi. So these are the atypical vertices that has low degree to either Vj or Vk. After cleaning this, what do we have? We have for every vertex here, it has linear degree to each part. Does it look familiar? We can now apply our lemma proved by dependent random choice. It says that if you have three parts, such that one part has mean degree linear towards the other two parts, we can then pass to a relatively large subset S. We can pass to a subset S. Let me draw it separately. Now we pass to the subset S, which is inside Vi, such that size of S is larger than is 1/2 times n over r to the power 2/3. So still way larger than square root n log n, or threshold on the independence number. So this is larger than alpha of g, such that we have linear minimum co-degree for pairs towards both parts. So here again, we have Vi, Vj, sorry, Vj, Vk. For every pair inside, you have, this is still linear co-degree. Okay, now what do we do? Since S, the size is larger than alpha g, there exists an edge uv in S. Let's take this uv edge. And we know for all pairs, including uv, has linear degree towards Vj and Vk. So let's take their neighborhood. Let me draw them slightly larger. So this is linear, their co-degree, co-neighborhood. Okay. Now what do we do? Okay. Let me call this Wj, Wk. So let Wj to be the co-neighborhood of U and V in Vj, and you define Wk similarly, okay? First, apply Ramsey to Wz. By Ramsey, we get that either you have a triangle in WJ, or you get the independent set of size square root of these times log of these. Well, which is, or alpha of G induced on WJ is omega of square root n log n, right? But what do we know? This is larger than, but this is larger than alpha of G. So we get a contradiction here in the second case. That means we must have a triangle in WJ. Let's mark this triangle. Let's say XYZ. So now take a triangle XYZ in WJ. What do we know? Well, okay, to be precise here, you need to do some cleaning to clean out some atypical vertices that has a low degree towards WK. This is okay because by slicing lemma, these two pairs still regular with slightly weaker parameter. So let's do that. So XYZ are typical vertices having a degree strictly larger than 2/3 by this density condition towards WK. So what we know is dx to WK, dy to WK, and dz to WK, they are all strictly bigger than 2/3 plus, let's say, gamma over 2 times WK. Okay. Then just by pigeonhole, we know that at least two of them will have linear co-neighbors, number of co-neighbors in WK. So let's say it's X and Z. We know at least two of them will have linear co-neighbor. Then you apply Ramsey again. This is linear, right? So by Ramsey, either you have a square root n log n independent set, which is not possible by our independence number, or you have a triangle inside. Now, a triangle together with this triangle, together with this edge, you get a K8. Done. Great. Okay. So the final step is to find triangle inside. Let me finish writing. Pigeonhole says, pigeonhole says at least two vertices, say x, y, in my picture is xz, have linear co-degree in WK. But then Ramsey one last time implies that triangle is this triangle in the co-neighborhood. So X and Z in WK. This one implies a K8 contradiction. Any question? All right. So there are many other applications of dependent random choice. As I said, you can refer to the survey of Fox and Sudokov for more examples. Now I want to move to a different method. So still probabilistic method, a sampling method. Okay. random sampling. Sampling. So what do I mean by sampling? I mean this simplest sampling. You have some probability distribution and you should just keep sample IID copies of random variable according to this distribution. Then by some law of large number, you'll know that. So, um, so let me make an example. Let's say we have a population, we have a country, right? Um, of people, men and women, um, with each one of them has a height. Then you look at the population mean, the average height of this country. Let's say it's 170. That's the average height, 170. And if you want to know the average height of this country of people, it's impractical to measure the height of each one of them. It costs too much time. And instead, what you do is just randomly sample a good number of people, let's say 10,000 people, and you measure their height and take the average. And the law of large number is basically saying this sample mean it approximates the population mean. Okay. So law of large number basically says if you sample randomly from a population, then the sample mean of whatever you want to measure from this sample. I use height, you can use weight, whatever parameters. Then the sample mean will approximates well the population mean. As long as, provided that the sample size is not too small. Provided that the sample size is large enough. Sort of. This is what it means. Now, how can we use this idea? Well, let me give you a concrete example. Let's start with you can get some nice approximation results. Let's start with one of the most fundamental theorem in convex geometry, the Carey-Theodori theorem. So what does Carey-Theodori theorem says? Zero. Accents here, right? I think. So this theorem is saying that you have a set of points in Euclidean space Rd. So the setup is we're given a set of points. Let's say x. I don't need to specify it actually. Okay. Okay, let me specify it just to illustrate. I don't need to. Okay. So we have a set of points x in Rd, a set of points. And then the setup is you have another point in the convex hull of x, in the polytope generated by x. So you take for any points P inside the convex hull of x, convex hull means the convex combination of points in X. Then actually we can find the subset of X of size at most d plus 1 such that P already lies in the convex hull of these subsets. So there exists X prime in X size d plus 1 such that, oh, oops, what did I do? Such that P already is in the convex hull of X prime. So you don't need all the, when you take the convex combination to, when you write P as convex combination as points in X, you don't need all points in X, you just need d plus 1 of them, okay? But sometimes the dimension d could be large. So the problem here is that sometimes the dimension d could be large. But first of all, this d plus 1 is optimal, the remark. D plus 1 is optimal bound. Okay? We cannot hope to find a subset of size strictly larger, strictly smaller, whose convex hull contains this point P. So the problem here is that when dimension D sometimes could be large, then X prime is still quite large, right? Could be large. So X prime still expensive. Okay, expensive means it's large. Then computationally, it's hard to find such X prime. What do we do when something is too large? We say, okay, since this bound is optimal, we cannot write P exactly as the convex combination. Can we at least approximate P using smaller convex combination of points in X? And the answer is yes. That's the contents of approximate Carathéodory theorem, proved by about 10 years ago. So let's first recall the for every P, recall. For every P at least 2, we induce, we have the P norm, the little P norm. So if you have a vector, let's say if you have X in Rd, how we define is X in Rd, then the little P norm equals to sum of xi to the P, I equals to 1 to D, then you take the Pth root, okay? So usually we care about Euclidean norm. You take these two. Now we can approximate in Euclidean distance to P up to any small additive error with a number of points that's independent of D. So can we, so here's the question. Can we approximate the point in the convex hull using a set of size independent of the dimension? That's the question earlier, right? So the answer is yes. We can approximate it. Here's the theorem proved by Barman. This is the approximate Carathéodory. Says the following: for any set of points x1 to x, let me write out this point. This is point x1 to xn in Rd. Let's say they are in a unit ball And we work in the more general case, not only for so here, maybe let me use Z. I use the LP norm P down here. Let me not repeat a symbol. So we can approximate this point Z. Not only we can approximate in the 2 norm, we can approximate by any P norm. Okay, so let's normalize it so it's inside the P unit ball. So what it means is that, i.e., for every xi, its P norm is M-1. Okay. Then what other setup? You take some epsilon. This is the additive error. You want to get close to the point. Now you take a point mu inside the convex hull of X. Okay. You fix your favorite norm P. We can approximate this point mu inside the convex hull by, so there exists k points where k is at most 4p over epsilon squared points. Let's call this point y. This is a multi-set, so some points in xi could be repeated in y, okay? So this is a multi-set. So it consists of some xy, some xi, but xi could be repeated in here. In total, at most k of them, such that if you write mu prime to be the average of these points, then mu prime is a good approximation of mu. In LP norm is less than epsilon. This is the approximate Theodoric theorem. So as I said, this is our population, right? Earlier. So, well, sort of. This is our population. Then you just, as long as you sample, and this is sort of the population mean, but weighted by this convex combination. So here, as long as you sample enough large, sufficiently large sample size, this is sufficiently large, then you look at the sample mean, it approximates the population mean well, right? So this is sample mean, right? And this is population mean. Population mean. Okay. Any other comments I want to say? Right. Remark. Once again, the nice part here, let me highlight it here, is that this bound number of points we need is independent of D. The important part in this approximation is the number of points needed, which is 4p over epsilon squared, is independent of the dimension D. Okay, so you only need, we fix a constant p, constant number of points to approximate up to epsilon error. The idea is very simple. I already told you the idea. You do random sampling and then use some sort of law of large number. So the idea is we're gonna first, because it's in the convex hull, so we can expressing mu as convex combination of points in X. This then naturally induce a probabilistic distribution over X. Let's call this probability distribution. Then we're going to do sampling according to this distribution. Okay? Well, actually, this probability distribution over X will produce a random variable with mean mu, or point mu. Then you do sampling, sampling IID copies, IID copies to approximate, and use sample mean to approximate. That's the idea. So one thing we have to be careful here is that the naive way is to do things coordinate-wise. This is points in RD, right? If you want to approximate in every one of these D coordinates close enough, and then together you say the norm is close, the distance, P distance is close, you have to apply union bound. Then that will give us some bound involving some function of D here, because you use union bound over D. So instead, we're going to use, we don't want to use Chernoff or Hofting and the union bound. So cannot do it coordinate-wise. And apply union bound over all D coordinates, all D dimension. Okay? Because then it's not dimension 3. Then it's not dimension 3. So instead, we're going to use this another inequality called Khinchin's inequality. Let me state this inequality. Actually, I will state the corollary of Khinchin's inequality. It says the following. We have some points, xi, given points for I from 1 to m. You have some points xi in Rd. Okay. Then you also have some random Rademacher random variable epsilon I. So this is Rademacher random variable. All it means is that it equals to plus minus 1 with probability 1/2. Okay, very simple. Then we have the following. We can bound the P norm of the Rademacher sum in expectation. If you look at the Rademacher sum, that means we sum up xi, but multiply by epsilon I. You multiply by a random sign. And look at the P norm. This is at most square root P times sum okay, so we have this inequality. Let's take it for granted for now. Later we will see a proof of the original version, which implies this corollary. Okay. So let's carry out this idea. Let's now prove this approximate Curie theory. Once again, what it says is that you have a set of points in RD. Now, take how well you want to approximate a point mu. Take a point mu in the convex hull, and then take your error term. You want to approximate mu in P norm up to error term epsilon. We claim that we can take the mean of at most constant number of points that depends only on this P norm and epsilon. In particular, 1 over epsilon square, number of points. Let's first write it as convex combination. What it means is that we write, since it's in the convex hull, write mu to be the sum of alpha I, xi, the points in X, where alpha I are all negative, and sum of alpha I is 1. This is what it means by convex combination. Now these, in particular, induce a probability distribution. Let's call it alpha, right? This is a probability distribution of a random scalar over n choice of scalar alpha I, such that it takes this alpha takes alpha I with probability. No, what I mean is the probability of, you have this, if you sample a random points v according to alpha, then v equals to xi with probability alpha I. That's what I mean. Okay, you have a natural random distribution. What's special about this random distribution? In expectation, that's the point mu that we want to approximate. Let's look at the expectation of v, where v is sampled according to alpha. This equals to, as I said, this is sum over all I from 1 to n. It has the probability that it takes x times xi, right? This is definition of expectation, which is sum of alpha I xi. That's exactly mu. Good. Now what we do is we sample large number of points, called IID copies according to alpha. Sample IID copies v1, v2 to the dot, vm by this distribution alpha. And we're going to let mu prime to be the sample mean. And we claim that this mu prime has positive probability. So it suffices to show the expectation. This expectation is over all choices of vi. Their sample mean v mu prime minus mu p norm distance. The p norm of their difference in expectation is at most 2 square root p over square root m. M is the sample size. Why is this enough? Well, if you do this, then you can take m, the sample size, you can take this many samples. If you take this many samples, what is this fraction? This fraction is nothing but epsilon, okay? Yes, that's correct. Then we have the expectation of this is epsilon. This means by first moment, we know that with positive probability, there exists an outcome of V1 to Vm such that mu prime minus mu p is m most epsilon. And that's what we want. Okay? So it's enough to prove this. Let's do that. So to apply Khinchin's inequality, let's look at here. This in particular is a symmetric real random variable because of this plus minus 1 with equal probability. So we first have to apply this, we have to first symmetrize our random variable to be of symmetric form to apply this. All right, this is a standard trick, how we can bound things using this Rademacher sum. So there's a standard trick. Now the idea is we're gonna write things in a symmetric form and use Rademacher's. Once you can write it in a symmetric form, we can bound it using Rademacher's sum. What do I mean by this? Let's see the details. Okay, so here's the claim. This is the purple part I'm saying. The claim is, so what we want to bound is this expectation, the p norm of the difference. So let's first write out what's this p norm of the difference. P norm of difference is, what's this mu prime? It's the sample mean. So that's the average of V1 to Vm. Okay. Minus mu. Okay. This standard trick is that if now we take, this is at most, here's the trick, at most Vi prime, epsilon I Rademacher random variable, 1 over m, sum of I to 1 to m, epsilon I Vi minus Vi prime, P norm. Okay, where V1 to Vm prime, this Vi prime, again, IID copy drawn from the distribution alpha. They have the same distribution as Vi, and they are independent of each other. That's what it is. So we managed to write what we need to bound by this Rademacher sum. It's very symmetric now. Let's finish the proof using Khinchin's inequality. Then we come back and see how we do this symmetrization step. So finishes the proof. This claim will imply well, actually implies this step, right? Implies that the thing we want to bound is at most these. So First, by the claim, this is at most this guy. But this guy, let me use triangle inequality because P is a norm, to break this into two parts. So triangle inequality and the claim. This is at most the 1 over m. I can extract the scalar out, right? No problem. Expectation of vi prime, epsilon I, sum of epsilon I vi plus sum of epsilon I vi prime. This is nothing but triangle inequality. Now, look, we decouple, these two are independent, vi prime. So they have the same distribution. These two is the same. So we just get rid of 1, multiply by 2. This equals 2. By the independence, 2 over m, expectation, vi, epsilon I, sum I from 1 to m, epsilon I, vi, p norm. Now you use Khinchin's inequality. This is at most 2 over m. Khinchin's inequality is saying that the p norm of the Radmacher sum in expectation is at most square root p times sum of vi's p norm square divided by 1/2. Okay, but we are in the p unit ball. That means this is at most 1. All right, vi is in the p unit ball. If this is at most 1, in total, this is at most m. So this is at most square root m. We are done. We are left. So this is just calculation. We are left to show this this symmetrization part. Now, proof of claim. How do we symmetrize things? Well, so we start here. Oops. Okay, let's start here. Well, what do we know? We know that vi prime, because vi prime also sample from alpha, the we can write mu as actually the average, the expectation of 1 over m sum of vi prime, right? This is what we know. Expectation of vi prime is mu, so their convex combination, of course, in expectation is also mu. No problem. So let's rewrite mu as the as this expectation. So we get this is And actually, I would like to um, move this to, let me do this. It's slightly longer. Let me move vi prime to the front, parenthesis, 1 over m, sum of vi minus 1 over m, sum of vi prime. Start to look symmetric, right? P. So all I did is write mu as this. Okay, here. Then I move expectation to the front. It doesn't affect this one. These two are independent. Good. Now, now this we use Jensen's inequality. What is Jensen's inequality? Jensen's inequality. Convexity, right? So this is our function f. That means this guy here is the average of the function. And this thing down here is the function of the average. Yes. So function of the average is at most average of the function. This is Young's inequality. Now apply with this guy being our random variable x and our function f is the p-norm function. Okay. What we then have is this is what? This is function p-norm of the average of this random variable, right? Now it's at most average of the function. So this is at most. We move average out, vi prime, and put the function in. 1 over m, vi. Let me write vi minus vi prime. Okay. P. Jensen's inequality. Now, this is a symmetry random variable. Symmetry means, this just means, so if a random variable x is symmetric, then that means x and negative x, they have the same distribution. Okay, in particular, any symmetric random variable has been 0. And what's more important is that, let me use y maybe. For a symmetric random variable, if you look at its expectation, you can you can multiply by a random sign, Rademacher sign. Okay, this is Rademacher. What this means is that now we can add the random sign equals to expectation of vi prime, epsilon I, 1 over m, sum of epsilon I, vi minus vi prime. And that's exactly what we need to prove, right? That's the bound we have here. That's it. Now let me leave as exercise. For you to prove this infinity version, this is exercise to show the approximating infinity norm. It says that we have a point x, our usual points, x1 to xn in Rd. Okay, I need to finish this. With infinity norm at most 1. And you take your favorite epsilon bigger than 0. Then the conclusion is, for any points in our convex hull of x, there exists at most big O of log n over epsilon n squared points in x whose average mu prime up to multiplicity, up to taking, you're allowed to take a point multiple times, whose average mu prime satisfies mu minus mu prime can approximate in the infinity norm up to epsilon. Okay, the hint is just apply Hofding, for example, and union bounds. Let me end the class slightly early today. That's it. We're gonna continue next year. Okay. Happy New Year. See you guys next year.